next
What is that?
paper is on the topic
The
closely
mic.
modifiers.
Oh, yeah. I'm taking the mic.
Software architecture and how we can build in
Thank you.
that really works across different machines. So the paper is Distributed System Development with ScalaLoci, and it's by Pascal Weinberger, Gearpump forward, and Guido Salvaneschi.
Thanks for the introduction. So, hello everyone, and this talk is about ScalaLoci, a language to ease the development of generic distributed systems. And this is joint work with Mikko Köhler and my advisor, Guido Salvaneschi. So let me start with a quick comment first. So yesterday, Heather Miller gave this talk on what happened to distributed programming languages. So here we are to let you know that we're still alive in very good health. So thank you for asking. But honestly, there are reasons for asking this question. So let's start with that part first. And to do that, let us have a look at how state-of-the-art real-world distributed systems are developed today. And what you can see here is an example for this. So this is actual code taken from the Apache Flink stream processing system. And of course, you are not expected to read this code. In fact, you shouldn't, because I already did it for you. So here are two components, a red one and a blue one. And they may run on completely different hosts. So these components are part of Flink's task scheduling and task deployment logic. Those are basically two actors that are communicating with each other. And as usual in actor systems, they communicate by exchanging messages. So here I mark all the places where messages are sent from one actor to the other actor. And just from looking at the code, it's completely unclear where these messages are handled, or if they are handled at all. So I manually checked where these messages are processed, and this is what you can see here. And you may wonder if this is really the most intuitive way to model data flow in a distributed system. And this is also just a small part of the system, and there are many more components that essentially communicate in the very same way with each other. There's a class of languages called multi-tier languages, which allow you to implement a distributed application in a more coherent way. And multi-tier languages emerged in the web setting to ease the development of web applications. So the idea there is that you write your entire web application in a single compilation unit, and then the compiler generates the code for the client and for the server automatically. And since these languages focus on web applications, this in particular means that they only support the client-server model, which is not enough for many types of real systems, like the one I've shown you on the slide, which consists of multiple different components. So ScalaLoci addresses multi-tier programming for generic distributed architectures. And we model communication between the components using multi-tier event streams that can cross different hosts. And the way we achieve those features is through placement types. So let me quickly introduce placement types to you. So since ScalaLoci is a Scala embedding, basically, let's have a look at some Scala code. So this is still standard Scala, and by its type, you can guess that this message value is some kind of event stream that carries strings. And this could live on any component. So placement types allow us to talk about placement explicitly. So here we say that this is an event placed on some registry component. So the complete type of message is event of string on registry. And this means we encode placement information at the type level. Now, of course, we also want to place actual code that gets executed on a specific component. And we do this by wrapping code in a placed expression. So this way, placement of code is lexically scoped. So in this case, we call getMessageStream on the registry component. And because by the type ascribed explicitly to the expression, we know it is placed on the registry. And we can then freely define the components of our distributed system as Scala traits that inherit the peer trait. So we now have a registry peer and a node peer in our distributed system. So let's keep using our example with this registry and node peer. And here we can specify the distributed architecture using those peer types. The way we define the architecture is by specifying ties between peers. So since the architecture is encoded into the Scala type system, we specify ties by using this tie type member. So in this case, we define a registry that has a multiple tie to nodes, and a node that has a single tie to the registry. So this type-level encoding is the mechanism that we use to support different kinds of distributed architectures. So this architecture specification that we can see here models this type of architecture where nodes always connect to a single registry, and the registry can connect to multiple nodes. We can then extend the specification for the node peer, for example, such that it also has a multiple tie to node, which means we model in this kind of different architecture where nodes can additionally connect among themselves. So using this kind of architecture specification gives us a quite flexible way to support different architectural models. And since this is all encoded at a type level, we can statically type check that remote access conforms to the specified architecture. And in particular, we treat remote access differently depending on the specified architecture. So the specification of placement and architecture has an impact on how values are accessed remotely. So here we have an architecture with a single node and a single registry. And then we have our message event stream that is placed on the node. Now we access message remotely using this .sLocal construct to make remote access explicit. And when we access message remotely from the registry, what we get is just a simple event stream. And this is the local representation of the event stream from the only connected client. And from the architecture, we know that there can only be a single one. So whenever this node fires an event, the event is propagated to the registry. Things become a bit more involved when the architecture allows us that multiple nodes can connect to the single registry. So here we change the architecture specification to allow multiple nodes to connect. So in this case, there may be different nodes which all provide their own message event stream. And the idea is that when you represent all nodes by the same type, you somehow want to treat them uniformly. And in this case, SLocal aggregates the remote values of all nodes. So what we get then is a mapping from remote references for the nodes to the event stream provided by every specific node. And thanks to the type-level encoding, remote access is statically type-checked based on the architecture specification. So now let's have a closer look at the communication between different peers. So in the end, peers have to exchange some kind of messages to communicate. And this kind of communication is often event-driven. So peers send events to other peers, which then somehow react to these events. And we've already seen event streams in the example so far, which we use to model this kind of event-based communication. So let's assume a simple event-driven application where the node sends some message to the registry processes the message and sends the result back to the node, where this then may be displayed in some kind of user interface. Implementing this locally could look like this. So we define the message as an event stream, and then we define the result as an event stream that is derived from the message stream. So in this case here, for every message event, we execute the process message function and send its result through the result event stream. And finally, we create a user interface that gets the result as an input. So now we want to place the different values on different peers. And to do so, we simply use the place expression to specify that message is placed on the node. And this placement is then also reflected in the type of message, which is now event of string on node. And in the same way, we place result on the registry and UI on the node. Now, message, which we know from its type, is placed on the node, is used in the second line in an expression that is placed on the registry, and similar for result in the third line. So by their types, we know those two are remote accesses. And remote accesses are explicit in ScalaLoci, so we use SLocal. So in this example, once the connection to the remote event streams are established, events are propagated across hosts. Now we've translated this example into a distributed application in a way that we do not have to deal with low-level communication primitives, and we can just simply specify the placement and the data flow in a declarative way. So far we were using this example of the registry peer and the node peer, where we placed a message event stream on the node and distributed it to the registry. Now let's put those things to use in a small but complete application where we use the event streams for communication across hosts. So here we implement a chat. where multiple nodes can chat with each other through a central registry. So first, we define the architecture, where we have the registry that has a multiple title nodes, and the node that has a single tie to the registry. And then we place the message event stream on the node. We've already seen this message event stream in the previous code snippets, which we use to express cross-host event-based communication. So we fire the event message for every line typed on one of the nodes. And then we access this message event streams from all the nodes remotely and aggregate them into a single event stream on the registry, which we then bind to this public message value. And finally, the nodes access this public message stream from the registry and print out every message. So this is basically all the code we need to implement a working chat application with data flow from the nodes through the central registry back to all the nodes. So we evaluated our design by looking into existing distributed systems, namely Apache Flink and Gearpump, to evaluate how ScalaLoci can be used in complex existing systems. And we also conducted an explorative study on some applications that we implemented in 22 variants. And here we experimented with different applications of different distributed architecture, for example, client-server applications, peer-to-peer applications, master worker patterns, and so on. And in the paper, we also discuss code metrics for all these variants in more detail. And here, I want to give you a high-level intuition of how one of the applications in our case study looks like and how ScalaLoci compares against other approaches. This is one of our example applications. It's a simple ping pong game where we started with a purely local baseline. And as the next step, we use ScalaLoci to implement a distributed variant. So the yellow parts are functionality that we added for multi-user support that was not there in the local variant. And the orange parts are the ones actually needed for the distribution. So here we could just reuse most of the code and only needed to add placement specification and remote accesses. We also implemented the same application using Akka actors. So here we have some more communication boilerplate for manually sending and receiving messages. And more importantly, we lose static type safety guarantees for remote access. So for Java RMI, we have a similar picture. Basically, it's just more boilerplate needed for the communication there. So let me show how we applied ScalaLoci support for generic distributed architectures to the Gearpump real-time streaming engine. So Gearpump was implemented initially at Intel and became an Apache project later. So here we re-implemented the worker assignment logic in ScalaLoci. So in Gearpump, a master proxy is responsible for assigning workers to masters. And we express those three components, the master proxy, the master, and the worker, using placement types. So the master proxy talks to multiple masters and multiple workers to assign workers to masters. And every master can then have multiple workers that are assigned to it. And it can also query multiple master proxies, which is used as a kind of backup mechanism if a master proxy fails. A worker, on the other hand, always refers to a single master proxy for its assignment. And it may or may not be assigned to a master. So there is some code in the Gearpump actors that deals with maintaining this kind of architecture. So for example, there is some list on the master code that is used to add workers when they are assigned and to remove workers when they are unassigned. And all this has to be done manually. So in ScalaLoci, we do not have to do this kind of manual bookkeeping. Here we can just simply specify the architecture in the peer types, and the framework keeps track of connected remote instances. So let me quickly come back to the Apache Flink task scheduling logic that we've seen on the initial slides. So here is the case that having distinct modules for every component of the distributed system and this kind of imperative message passing that leads to this kind of scattered data flow. And the data flow that you see here looks very complex, but actually this complexity is mostly accidental. So if you investigate the data flow more closely, you see that you could express it in a pretty regular style. So to bring some order to this chaos, we use ScalaLoci to restructure the components of Apache Flink into modules that are themselves distributed. So here we modularize not based on the components of the distributed system, but based on different functionality that should be encapsulated. So in this case, you see a module for the task deployment at the top and one for checkpointing at the bottom. So since these modules are themselves distributed by using placement types, parts of the code is still executed on the red component and parts of it is executed on the blue component. And this approach makes data flow explicit and easier to track since it is not interrupted by a manual message passing scheme, which also makes it easier for a developer to reason about the system. So this is just one example where we re-implemented some more components that are listed here, which are all part of the scheduling and deployment logic of Apache Flink. And in those components, we were able to eliminate non-exhaustive pattern matches and typecasts that could potentially fail at runtime otherwise. So we deployed Apache Flink with our re-implemented components on Emerson EC2 and ran the Yahoo streaming benchmark in the cloud environment. So here you can see the benchmark results, where we basically varied the number of worker nodes, and the Yahoo streaming benchmark measures latency. So the brown plots represent the unmodified version of Flink, and green is the Flink version with the ScalaLoci re-implementation. And what you can basically see here is that there is no real measurable performance impact for using our more high-level mechanisms for placement and communication. So for further details, I invite you to read our paper. There's a bunch of interesting stuff in there that I did not talk about here. So we show how fault tolerance can be achieved in our system, how we can deal with dynamic changes in the topology within the constraints of the architecture specification. We quantified the impact of ScalaLoci on the application design using code metrics, and we performed micro-benchmarks to evaluate the performance of our language implementation. Also, we give some further details on our implementation that supports different backends for the event system, and we also support the compilation to Java bytecode and JavaScript using the Scala.js compiler. So it is possible to implement clients that run in web browsers. We also formalize the language to prove our placement type system sound. So the implementation of the language and all the case studies and variants are available on GitHub. So if you're interested, please feel free to check out our GitHub page, scalaloci.github.io. So now let me conclude this talk. I presented ScalaLoci, a language for developing generic distributed systems using a coherent multi-tier programming model, where you can freely specify the distributed architecture, which allows you to place values on the specified peers using placement types and compose event streams across peers in a type-safe way that conforms to the architecture. Thanks for your attention.
Thank you. Questions?
Hi, thanks. You mentioned that ScalaLoci makes it easier for people to reason about the communication in their programs.
Mm-hmm.
How did you evaluate that?
Yeah, that's a very good question. So there are arguments made, right, that this kind of event-based programming that can define streams in a declarative way makes it easier to understand code, right? That there are like studies on that. We have a study that shows that reactive programming makes reasoning for users easier. And so this is in light of argumentation that we basically apply here that, this kind of declarative data flow that you can follow as a user is basically easier to read.
So you're basing this on theory from other work?
This is basically a previous work, yes.
Okay, thanks.
Did you point at someone over there first?
Go ahead.
Okay.
Next.
Sorry. Hi, very interesting. I happen to build a couple of distributed systems, and I'm wondering if it's possible to actually make these into generic components. Say that I have, someone has specified in ScalaLoci a core of a distributed system, and I want to add clients to it and introduce new links. Is there something I can extend, or do I have to edit the code that you wrote to put the extensions in?
So you're basically talking about having different modules of the language that you can compose?
Yeah, where the modules aren't aware of how the composition will work.
Yes, yes, yes. That's a very good point, and we should definitely explore more how a module system in a multi-T language could look like. And this is actually ongoing work that we're currently looking into. Yes.
Thank you.
Several years back, I've seen some papers on the X10 programming language, which built on Java and had places and asyncs and. So is there a connection between this and some of the ideas?
Between X10, yeah. So in X10, there's also a notion of placement in the type level. So there are some similarities, but the domain is completely different, right? This is like high performance computing, basically, and we are talking more about distributed systems. Yeah, but the idea that you have some notion of placement in the types, that's similar indeed, yes.
So every distributed language starts off simple, including yours. So have you considered how to accommodate different forms of multicast under different consistencies, back pressure on streams, a whole bunch of things where people want to reach into what you provide to do something different?
So basically, regarding consistency, we basically say we don't provide more than actual systems usually do. So we have like at most once delivery, FIFO between pairs and so on.
The multiplier of complexity once you do allow that?
Sorry, come again?
There's allowing that.
Yes.
Brings you into a Cartesian product.
Yeah.
Space.
Yes. Not sure I get the question, to be honest, but
maybe the question is as you have to have variation in more dimensions of the distributed system space.
Yeah.
Do you have the composition mechanisms in your language that allow that to scale linearly rather than quadratically?
Yeah. Okay. Yeah, I mean, these are definitely issues in distributed systems that needs to be addressed, but we currently did not yet look into that part. Yes. Yeah.
All right. So one question from Slido. Michael Meyer asks, a previous speaker asks, can you define changing topologies? And maybe you can answer this as we switch over.
Yeah, sure. So we have some constraint that we define statically and the architecture specification, but within the constraints of this specification, we can have changes in the topology, so we can have nodes leave and join dynamically at runtime. Yeah, sure.